Okay, so let's get started. I'm going to just cover the procedure and analysis method that we're going to use to do our report. And I know that a couple of your friends in the groups couldn't make it today, so I'm also recording a lecture. I'm going to put it online. I hope everybody can hear me. Can everybody hear me?
Yes.
All right, great. So I'm going to share my screen and describe a few things here. As you can see now that in the manual, the main idea behind this report, behind this experiment, is to determine the effectiveness of the heat exchanger, which is something like the efficiency, and to also perform an energy balance, so we know that energy conservation actually works. So these are two main objectives of the experiment. The effectiveness is a lot more involved because it depends on some key variables. So we're going to focus on the relationship between the effectiveness and a couple of key variables. The first one is called the number of transfer units, which is kind of a defined variable that tells us something about the design of the heat exchanger. It combines how fast the flow is moving, and it combines the geometry, how well the geometry is designed. So this is the NTU, the number of transfer units. And then the second variable is the flow rate, how fast we can flow. Depends on the pumping power and how much we want to spend, how much power we want to spend on pumping the fluid. So these are the two independent variables. And as a function of these two, we want to plot or show the effectiveness. So the summary is that the objective is effectiveness and how it depends on the design features of the heat exchanger, and then determining the energy balance and the accounting for the energy lost that's not accounted for. And then, of course, we want to assess the errors. Okay, so that gets out of the way. And then if I look at my screen here, then the requirement is we did two tests. And what we want to do, we want to perform an energy balance. We want to calculate the effectiveness and the number of transfer units. And then we are going to use heat transfer correlations, because we will find out that the NTU, we must calculate the heat transfer coefficient, which means that we're going to have to use correlations to get there. So there's a little bit long cycle until we determine the NTU. And then we calculate the effectiveness and compare the experiment to theory. And then the graphs that are needed for the report. First, we held R sub C constant. R sub C is the ratio of the hot stream to the cold stream. So we held that constant in the first test, and we kept them in sync as we change the flow rate. So for that particular test, we want to plot the experimental and theoretical value of epsilon as a function of NTU. So that's first requirement. And then for the other tests that we did, when we had Cmax was held constant, then we varied Cmin, which is the hot flow rate. So we vary this. And we wanted to plot Q dot, the heat transferred between cold and hot stream, epsilon, that's the effectiveness, NTU also, and we want to plot these three as a function of Cmin. Cmin is m dot C sub P. So it is like the mass flow rate of the hot stream. So we vary this. We see if it is slow, do things get better or worse? If it is fast, do things get better or worse? And we have three variables to plot. So we're going to try to produce three different plots for those. And then these three plots are going to be fitted to straight lines because they're coming from the experimental data. So we're going to fit those to straight lines. And the data is going to, because you repeated every experiment several times, so we have some statistical variation, and it gives us an error bar, and then we're going to put the error bars on these plots. So this is all. As you can see here, the data reduction that is required. So now I'm going to go to prepare you for how you do these point 1 and point 2 in here. So let's just share the screen. And the first part of this lecture is going to be on how to calculate the NTU. And as we will see, the NTU is an experimentally measured quantity, and it involves the heat transfer coefficients. So by definition, it's going to have the conductance times the area divided by Cmin. That's the NTU. So the bottom line here is that we know the areas, we know Cmin because we measured it, but we don't know the conductance U, capital U. So the part of that I'm presenting here is how to figure the conductance capital U from correlations. It's all correlations here. So the model that we use is that we have an inner brass tube and that has a hot stream, and an outer plexiglass tube that is transparent and it has the cold stream. And the dimensions are R1, R2, R3, as you can see here. You have those in the manual. And if you have a point inside here and the heat is being transported from the inside to the cold water, it has to go through a boundary layer on the inside, and then it has to go through the brass, and then it has to go through another boundary layer on the outside. So it has to go through three different pathways to make it from hot to cold. And each time it goes through that, we think about it as a resistance model, as if we're conducting electricity in a series of resistances, as you probably studied in heat transfer. So if the T hot is on the inside, that's the bulk temperature, then we have a temperature drop up to the surface. This point that I have here is on the surface of the brass on the inside. And then it goes through the brass through R2. And then this point is on the surface of the brass from the outside. And then it goes through another boundary layer until it reaches the middle of the cold stream, which is about right here. This is so this resistance model is acceptable. It's a mimicking of the complicated heat transfer process. And we calculate the resistances R1 and R2 and R3. R1 and R3 are resistance of the fluid. So these are controlled by convection. So we have to find the heat transfer coefficient and then calculate the resistances R1 and R3. R2 is pretty simple because it's the resistance of the brass. So it's by conduction. So if we go through that, the inverse of the resistance is the conductance, just exactly like in an electric circuit. So 1 over U is the overall conductance that we are trying to figure out, because that is going to be important in the NTU. So U times P. P is the perimeter, the inside perimeter where the heat is going. So if we take unit axial length, then U times P is like the conductance times the area of the unit axial length. So this 1 over this conductance is the resistance. So if you look at the previous R total here is R1 plus R2 plus R3. This 1 over conductance, total conductance, is 1 over the conductance 1 plus 1 over the conductance 2 plus 1 over the conductance 3. Conductance 1 is 2 pi RH because it's per unit axial length. So the area is 2 pi R1 times 1, and H is the heat transfer coefficient, which is defined as watts per meter squared K. So that's the conductance in here. And from heat transfer theory, the conduction through an axial cylinder, we know that the conductance is 2 pi K over natural log of R2 over R1. And then on the outside in the boundary layer, we treat it exactly the same as the inner boundary layer. The only difference is that H in is for the hot and H out is for the cold fluid. Everybody agrees with that? So let's say that I want now to go ahead and figure out what this value is. This is what I want, this capital U. That's the objective. Then I have to scratch my head. I have to put in K for the brass, it's no problem. Dimensions are no problem. But I need to figure out what is the heat transfer coefficient. And at that point, you realize that in heat transfer theory, when we come to fluids, then we use correlations because they're just too complex to find anything better. So we use correlations, meaning that we rely on other people's experiments that we put in some form that can be used. And the correlations we use for the heat transfer coefficient are based on Nosov number. So we have to go here, and we define the Nosov number as H times the hydraulic diameter over K. HV over K. So the Nosov number is the ratio of convection divided by conduction. So it tells us how much convection we would have in the fluid versus conducting the heat through the fluid. And usually the convection is much more. So the Nosov number is going to be probably like 20, 30, 40, 50. The higher it is, the better we're going to kind of remove that heat. So if we know the Nosov number, which we should, then we will be able to calculate H. So now you see the story is getting more involved. Like we wanted to have capital U, and then we found that we have to find H. And then H, we have to find the Nosov number. So the next step is to use a correlation for the Nosov number. And that correlation is, there's several in the literature. So if you go Google heat transfer correlation, there are several of them. And this one is acceptable for flow in round tubes. This is Likaratsis correlation. And it tells you that the Nosov number is a simple function of the Reynolds number, Reynolds minus 1000, times the Brentall number, which is a property of the water. It's a water property. And times the friction coefficient of the pipe over 8. And then you have the numerator also. You have to include the Brentall to the 2/3 and F of 8 here. So this is the correlation that is based on a lot of other measurements that were made and fitted to the data. If we want to find the Nosov number, we have to figure out what the Reynolds number is. And therefore, we need to calculate the Reynolds number for the fluid. Not only that, but we have to calculate the Brentall number, and then we have to calculate the friction coefficient. And the friction coefficient is given by a Pedicle formula that you will also use in another experiment, the pipe flow experiment. So it's a function of the Reynolds number here. So it all now boils down to figuring out the Reynolds number. So to summarize the story, you calculate the Reynolds numbers from how fast the fluid is flowing, hot and cold. You calculate the Brentall from properties of water. You calculate the friction coefficient as a function of Reynolds number. you calculate the Nusselt number, and then once you're there, then you're almost there. Once you have the Nusselt, then you find the heat transfer coefficient, and then you backtrack, you find resistances, and you evaluate the capital U that we're talking about. Okay? So to get to the Reynolds, we must calculate the hydraulic diameter of the pipe. Of course, if it is a round solid pipe, then or round hollow pipe, then the hydraulic diameter is the natural diameter of the pipe, which is 2 times r. But if it is an annulus or any other shape, we use the hydraulic diameter definition is 4 times the area divided by the wetted periphery. So if you apply this definition to the area of the annulus, the difference between the outside and the inside, and then you divide it by the wetted periphery or perimeter that the water is in contact with, you come up with actually 2R3 minus 2R2, which means D outer minus D inner. So it's pretty simple actually at the end. And the reason is that the two tubes are circular. If they were like rectangular, then you get a different result. So this is, we got the hydraulic diameter, and then we are ready now to calculate the Reynolds. But we found that in the Nusselt number, we need also to calculate the Prandtl number, which is a property of the water. And the Prandtl number is defined as Cp mu over K water. This is the conductivity of water, thermal conductivity. And the way that the physical meaning of Prandtl is that mu is like a viscosity. So it's like a viscous diffusion of the particles of the water. So the particles of water are just moving around. And K over C sub P is proportional to the thermal diffusivity. So this is how fast heat is diffusing. So the ratio of mass diffusion divided by thermal diffusion is the Prandtl number. And that doesn't depend on the geometry. It's the property of the water, and therefore we have tables, and we can find the Prandtl number for any given temperature from the properties of the water. Okay, so now to continue, we need to calculate the Reynolds number for the hot and for the cold. So the symbols we use is Reynolds. Hot, H is hot. Reynolds number is the ratio of the momentum divided by the mass diffusion. So it is rho times the velocity times the diameter, hydraulic diameter, divided by the viscosity. So rho VD over mu H. So it tells you Reynolds, high Reynolds number, it means that the fluid has a lot of momentum, just moving very, very fast, compared to eddies or diffusion across its main transport line, which means that high Reynolds number are consistent with turbulent flows. And roughly when you have Reynolds number in the thousands, then you know that you have a turbulent flow, and that's what you're going to compute for the water properties that we have. So we need to compute the velocity in the inner tube and the velocity in the outer tube. And the velocities are the mass flow rate that we measure, because we measure the mass flow rate in kilogram per second, and divided by the density flow of the water times pi r squared. So if you look at it, the velocity times pi r1 squared is like a volume swept by the water in 1 second. So in 1 second, as the water goes through, you get a slug that has a volume of pi r squared times v. If you multiply that volume by the density, you get a mass. and that is the mass flow rate. So the mass flow rate is equal to the velocity times rho times pi r1 squared. And therefore, we use our measurements for m dot, and we can determine the velocity. And we do that for the hot stream, and we do that for the cold stream. So up till here, we determine the Reynolds number, Prandtl number, Nusselt number. Once we have the Nusselt number, we can calculate the heat transfer coefficient. There's a little twist in this story still, and that is the correlations for Nusselt number that we have in the manual. They are made for tubes that have kind of uniform temperature. They don't have like temperature gradients, and also they're all round. They don't have annular. They're not annular. So we have to correct for, especially for the cold stream, to correct for the annular effect. And also we have to correct for the variable viscosity effect because we have temperature gradients. So we have two correction factors. We take the Nusselt number that we computed, and we multiply by this R2 by R3 to the minus 0.16. This is the correction for the annulus correction. So going from a round tube to an annulus, we just have a correction because it's different geometry, and that's what the experimental data has been fitted to. The second correction is that as the temperature changes from the middle of the tube to the surface of the tube, then the viscosity of the water will change accordingly. So the viscosity is a function of temperature. So the Nusselt number that we compute is for the middle point of the water where we measure. But on the surface, the Nusselt number is going to be slightly different. So it will be the Nusselt number in the center times the ratio of the viscosity of the water at the surface, S the surface, divided by the viscosity of the water at the bulk. So that ratio is dependent on the temperature. So we have to look up the dependence of the viscosity of the water on temperature, and then estimate the temperature of the bulk, and estimate the temperature of the surface, and then take that ratio and insert it here. So it gives us a little correction. Similarly for the cold stream. So that's kind of really the longest part of the calculation is to get to this. Like we wanted to have capital U, then we have to get H, and H we have to find Nusselt, and Nusselt we have to get the Reynolds and the friction and the Prandtl, and then we can use our measured values of mass flow rates to kind of initiate the process of getting Reynolds. And then at the end, we have to make a couple of corrections to make sure that the Nusselt number is consistent with the real changes in the gradients in the temperature and the annulus. Okay. So this whole part that I explained is just to calculate capital U. Now we're going to go on to simpler areas, which is really how to calculate the effectiveness of the heat exchanger so that we can plot it as a function of NTU. And the NTU, as you notice, it is mainly related to this capital U that we were talking about. So once we find the NTU, then we want to find the corresponding effectiveness of the heat exchanger. So let's do that. So if you look at the cold tube on the outside and the hot tube on the inside, the heat flow flows from the hot to the cold through the brass. So the middle is the brass. And the difference in temperature between the central point in the hot flow and the central point in the cold flow That difference in temperature, we're going to call it theta. So here, this difference here is going to be called theta. So if you have parallel flow, the temperature of the cold is going to rise, and the temperature of the hot is going to decrease. And the difference between them, theta, is a function of position. So x goes from 0 to 2.5 meters. So it's kind of along the heat exchanger. For counterflow, you get similar behavior. So you have theta. So the focus now is on theta, the difference between mid to mid, hot to cold. Right? And what we're going to do is we will do a simple heat balance. Heat balance is like energy rate or power balance over a small section. So we're going to take this small section that is delta X, and then the heat that is transferred is, the heat is lost from the hot stream is m dot C sub P for the hot. And the heat that is gained by the cold should be m dot C sub P for the cold. And the heat that is transferred between them is dependent on the three resistances that I mentioned, R1, R2, R3, because it's going to go through. So if you think about it, there are three different ways that you can describe the power that is changing. We can say the power is lost from the hot, the power is gained by the cold, the power is transferred from the hot to the cold. Three different ways. And that's what we have here. Delta Q dot, lost from the hot, negative, gained by the cold, positive, transferred through the resistances. And now we are not going to talk about R1, R2, and 3. We're going to talk about U, the capital U, which is the summary of all of the inverses of the resistances times the area, which is P delta X. And theta is the difference between the hot and the cold. Capital C is m dot C sub P. So this is the key equation here in the theory part. And this I can split it into two equations. If I take this part here and equate it to this side, I get, and divide by delta X, I get dt by dx hot as equal to minus, because I have a minus here, U times P divided by C, like I take C on the other side, C hot in this case, times theta. So I have dt by dx hot minus UP over C times theta. Now if I take this term, equate it to that term, I can derive another equation, dt by dx cold, dt by dx, like I take dx, take it down here, is equal to UP over C cold theta. So you see now too many symbols, T, hot, theta, T, cold, theta. We don't want to have too many symbols. So what we do, we recognize that theta is actually a difference between hot and cold. Therefore, if we subtract this, actually this subtracted from the hot, then that subtraction is going to give us d theta. And therefore, if we subtract left side from left side, right side from right side, then we get d theta, and then we take this capital theta, lowercase theta, and put it downstairs. So it'll be d theta by theta is equal to minus UP times 1 over C hot plus 1 over C cold dx. And that is the describing differential equation that kind of tells us how theta behaves as a function of x. Because we can integrate it from 0 to L on the right side, and from inlet to outlet on the left side, you get natural log theta out divided by theta m. So this gives us the distribution of the temperature difference. And once we have now C hot and C cold in this equation, then we would like to replace them with the original definitions, which is m dot C sub P. for the hot and the cold. And that gives us this Q dot. The 1 over C hot is, this is the delta T hot divided by Q dot, because we have Q dot will be m dot C sub T times delta T. So we can replace 1 over C hot by this ratio, 1 over C cold by this ratio, substitute back and get finally this important equation that the overall heat rate that's transferred is the overall conductance, which we labeled to calculate earlier, times the area through which the heat is flowing. And the area, we can take the area of the inner, like you have a cylinder, so you take the area of the inner cylinder. You have L, and then you have 2R1 as you have a diameter of 2R1. So the pi D1 times L, that's the area through which the heat is flowing. And this kind of form that comes here, you probably saw it in the heat transfer course, this form is called the logarithmic mean temperature difference, LMTD. So the end result is that Q dot would be equal to U times A times delta T Ln. And again, now you notice here in this form of the energy transfer, the key is to finding this capital U that we discussed earlier. Now, I think we are pretty much done with the theory. Now we're going to try to see how we will calculate the effectiveness, the number of transfer units, and how we're going to relate them to one another. So the effectiveness is defined as the actual rate of heat transfer, Q dot, divided by the maximum possible that can be transferred from the hot to the cold. And the number of transfer units is defined as the rate of heat transferred per unit degree, like UA times, we have delta T now is 1 unit, so U times A, divided by the heat exchanged per unit degree, which is Cmin, and we have again 1 unit degree. So that's kind of a definition that is kind of made up definition to produce this parameter. It's a parameter in which it tells us a lot about the heat exchanger. It tells us about how fast the fluid is flowing and how effective we are actually moving things around so that the heat can be transferred in this conductance. And it tells us about the heat flow, the mass flow rate, as this ratio can be a measure of the actual geometric design that you have for the heat exchanger. And we define the R sub C as the ratio of Cmin over Cmax. So what we need is to determine epsilon from the experiments, determine NTU from experiments. So epsilon from experiments will be Q dot. Q dot is m dot hot times C sub P for the hot times T hot in minus T hot out. That's pretty easy. But Q dot max is the maximum possible amount of heat that can be transferred. So in this case, if you imagine that the hot fluid and the cold fluid will come in, and the heat doesn't wait until the end to be transferred. If it is magically transferred from the hot to the cold immediately upon entrance, that would be the maximum possible that anybody can design for. It's hypothetical, of course, but it's a reference. So this way, we can calculate the maximum possible from the inlet conditions, and we can calculate the actual transfer from the difference between inlet and outlet. And the NTU, of course, we discussed how to calculate it. So NTU is U times the area, PL, divided by Cmin, and P perimeter times L. Cmin is m dot C sub P. So all of these are now available to us experimentally. We spend a lot of time on U. This is geometry. This is mass flow rate that's measured. C sub P is from the properties of the water. So are we okay now? We can calculate the two key parameters, epsilon and NTU from experiment for any condition. Now, how do we relate them? In order for us to relate them theoretically, we have to go back to this describing equation that we had here, and this describing equation, differential equation that we had. So we're going to manipulate it so that we can produce a relationship between epsilon and NTU theoretically, because NTU is defined and epsilon is defined. So now from this equation, we just kind of move things around until we get the two definitions to relate to one another. And that's what we did here. So this is the equation. So we extract C cold outside, so UA over C cold, and rearrange here. Then U A, actually this should be, UA over C cold here is the NTU. So you have the NTU, and then you have 1 plus R sub C, and then you have log, natural log of theta 0 over theta out over theta in. So you rearrange it this way, and then you substitute now what is theta in and what theta out, and then this equation produces equation 18, which is a purely theoretical relationship between epsilon and NTU. And this relationship is good for parallel flow. So this is what we described here for parallel flow. We're not going to go through more theory because I'm just kind of giving you the briefest possible theory that's necessary for the experiment. So for counterflow, we have, again, another relationship between the NTU on the right and the effectiveness on the left. So if we know the value of NTU from measurement, we know R sub C from measurements, we can plug them in here, and we get a theoretical value of epsilon. So in other words, we can calculate epsilon two ways. One is measurements, which is the measurements of epsilon is this way, the Q dot divided by Q dot max. This is pure measurements. And one is theory, which is an equation. So we have the NTU and R sub C, you get epsilon. So that's kind of the relationships that we needed to plot epsilon as a function of NTU, both theory and experiment. The heat balance is, so I'm just summarizing the experimental analysis. Now the first step is the heat balance. Q dot hot is M dot C sub P T hot in minus T hot out. We know all these quantities from measurements. So that we can calculate this and this and see the difference between them divided by any one of them, either Q dot hot or Q dot cold. And that ratio is going to give us an indication of how much percentage of energy is wasted or not accounted for. And the effectiveness is actual divided by maximum. So actual is, we just have M dot C sub P on the top and the bottom canceled out. So we have M dot C sub P disappearing. And therefore we have T hot in minus T hot out divided by T hot in minus T cold in. So this is all in the conditions. There's a difference between in and out. We have these four measurements here. So for all practical purposes, we now can calculate the energy balance. We can calculate the experimental effectiveness. And also we can calculate the number of transfer units. You can see that in a few minutes you can get the energy balance. Few minutes you can get the epsilon, but in a long time you're going to get the NTU. The reason is because you have to calculate all these correlations and find capital U and then add them together and then make the corrections and all of this stuff to get NTU. So at this point, we are done because we have the energy balance, which is the first objective, and the effectiveness calculated it. And then we have the theory. The theory is right here. These two equations, 18 and 19. That is the theory. So we're going to compare to those. And then we were going to do some error analysis. So what I wanted to show you is how the results are going to look like just for your guidance. When we plot the NTU, the epsilon versus NTU, we have to have two values, one experimental and one theoretical. The theoretical, of course, is kind of a continuous line because you just plug into equation 18 or 19 and you get a line. But the experiments is what you actually measure for epsilon. And that has to have an error bar on it. So you can imagine you have a line from equation 18, 19, and on top you have some points, and each point you have some error bars on it. So this is one type of graph. The other type of graph is finding Q dot and NTU as a function of C min. So these are going to be straight line graphs. So you're going to have measured values with the errors, and then you're going to connect them with straight line and do some error analysis. So there's a little bit of error analysis for a curve fit. So if you have a linear curve fit, you have in the manual how to find the error bar on the curve fit and make the data lie on that straight line and have this error. We have an example of it. So now I'm going to just show you some examples of calculations that you can read on your own here. The numbers are for the Q dot are between 2.5 to 3 kilowatts. So you can see here, and the difference is very small. The epsilon is pretty straightforward. You get like 60% or so, 66%. You use equations 18 or 19. You get, depends on parallel or counter, you get another value for epsilon, then you compare this one to this one. You can see the small, not too far. And you're going to do that for every condition that you have. The longest calculation is finding capital U. So you're going to start with V, cold, V hot from the mass flow rates. You're going to find the Reynolds numbers. We are in the thousands, 17,000, 9,000. You're going to find the friction coefficients. There's a couple percent. You're going to find the Prandtl numbers at 5 or 6 in that order. You're going to find the Nusselt numbers. As I said, their convection is pretty strong, so it's in the 70s to 100s in that case. And then you're going to make corrections to Nusselt and a couple of corrections. And then finally, you get to the promised land of finding capital U times the perimeter, which is the number that you need, so that you can calculate the MTU. So all of these shenanigans is to calculate this number 1.814 from the correlation. Once I have NTU, I can plug it into equation 18 or 19. And because here, if I have the NTU, then I can plug it into any one of these two equations, this one, also C, this one, and I produce a theoretical value of epsilon that I can compare to experiments. So these guys I have here, and these are the straight line fits that we have. And now I'm going to just show you an example of a report for guidance. So for guidance here, you see that a good example of a two-stream heat exchanger report. And we have divided the grades into different levels so that every grader can be accurate. And we provide guidance. You can see my guidance on the abstract is that it's good, but not good enough because you have to say what you measured, what values of things, what kind of quantitative information you got out of this experiment, and so on. You have units. You have to be careful with the units. They did not put the units in here. Introduction goes from very general, like what a heat exchanger is used for, parallel, counter, cross flow, regenerators, all kinds of applications. You can spend time discussing these here, and then you finally decide what the objectives are. You can talk about the objectives and how you're going to do the setup, so what is the setup for the experiments? That's what the introduction is for. Theory, we discussed this, so I'm not going to go through that. Apparatus is from what you have, but then it would be nice if you have a drawing by yourself or a block diagram for the experiment or apparatus, your own drawing. Procedure, you paraphrase. Observations is any observed fluctuations or errors and so forth. And then the calculations, these do run through one calculation clearly by yourself, line by line. Like what is the average hot, what is m dot, what is units, what is q dot hot, just in great detail to convince the reader that you actually did the measurements for one case and you calculated everything as shown here. Velocities, Reynolds, and so on. So you can see long calculation to find capital U, and the Nusselt numbers, and then the productions, and so on. And then you can see the equation. Error analysis, I give you two methods. One is by taking derivatives and adding the errors as quadratures, like just the squares of the errors and take the square root. Or you can do it with the perturbation method that I showed you as a table and changing the errors in the temperatures and in the mass flow rate. Like the mass flow rate, the error is about 2% of the maximum photometer reading, and the error in the temperature is like 0.2 Kelvin or so. You have those in the manual. And then you propagate them to determine what is the bias error, what is the precision error. And then the results, they have graphs, but they didn't really, it's kind of an old report, so they didn't have MATLAB to show very nice and neat values. So it should be effectiveness versus MTU. And they have scattered numbers here. It's like, looks pretty bad. It should be, the theory should be kind of a line going through, and then the experiment should be a dot, and then an error bar on the experiment. That's the way that we'd like to see it. If you need to, don't crowd one graph with so many things. Like they have 4 different things on one graph. You should maybe split it to 2 graphs easily. Here is the Q versus C min. And then on the right side, they have epsilon and NTU versus C min. I would prefer to have Q versus C min on a one graph, and then epsilon and NTU versus C min on another graph. Again, the idea is so the reader can understand what he's seeing. Like here, there's a bunch of things kind of plotted on the same graph, and you don't know which is which. You have to really spend a lot of time to figure out E parallel, E epsilon counter, and so on. So you can actually make them neat and separate them, or you can use subfigure. I have in my lectures on MATLAB how to produce subfigures. You can produce 4 different subfigures, and that you can display different things very easily. Now this is kind of nice because they have Q versus C min, and they have actually finally figured it out. So you have the dot, and you have the error bars, and you have the coefficient of precision that they kind of use the straight line fit to the data, and they plotted things. But as you can see, it's kind of a mess because many things are plotted again on the same thing. There's no need for that. You can split it into 4 figures or subfigures, so it looks kind of cool and clean and easy to read. Okay. I guess that's kind of a general discussion, and we have now all of the information that we need to be able to produce a good report. And by the way, we have 1 week from today to submit the report. So you have this coming week and weekend, and then you'll be able to submit it by Monday of next week. Are there any questions? Okay, so if there are no questions, I'm going to stop here, and I'm going to stop.